All right, welcome to building an OpenGL game engine in Visual Basic.net. Part 1, infinite scrolling background. I'm really excited to be making this video. My name is Daryl and I've been a Visual Basic programmer for over 20 years professionally and 30 years if you count some basic code I wrote when I was just a little kid. I'm completely self-taught, and what we're going to be doing today is creating your first OpenGL program using Visual Basic.net in Core 5.0. First, before we jump into the code, I want to talk about some of the concepts around OpenGL programming. First off, it's very different than what you're used to. If you've been programming outside of the GPU land for a long time, you need to think about your code in two lights: CPU code and GPU code. All of your Visual Basic code is going to be written against the CPU, but you'll be sending commands to the GPU. So you have to keep in mind these two beasts, the CPU and the GPU. One major difference you will need to wrap your head around is the differences between the coordinate system. In CPU land, the point 0, 0 refers to the pixel in the top left corner of the image. But in GPU land, 0, 0 represents the center of the screen. In CPU land, 1, 1 would be the pixel at 1, x1, y1. However, in GPU land, 1, 1 represents the top left corner of your screen. And while we're thinking about the GPU, you should dismiss right now the thought of anything being in pixels, but rather in percentages of the screen is still closer but not quite the same, as -1 would be the bottom right corner. So the percentages, that's like 200% range to fill 100% of the screen. But it's better to think about it as percentages than it is pixels. Now this idea is very important. Think about it this way. Every user using a program can have a different monitor resolution. So do you want your image to be a specific number of pixels, or do you want it to fill a percentage of the screen? You don't really care about how many pixels a user has. Just think about that you want your image to fill 100% of their screen, and mentally you're going to be ready to be a GPU programmer. So keep these ideas in mind as we jump into this program. Let's start by creating a new project in .NET Core and adding an OpenGL through the NuGet packages. So I'll just show you real fast here. I've created this new program. If we go into properties, term framework is .NET 5, which is now what they've renamed .NET Core. And let's add the dependencies. First off, .NET Core doesn't have access to bitmaps, so we need to add bitmaps. So that's drawn. System.drawing common. If we go through all these things, you'll see that it's got .NET Core right there. And then we're going to go to OpenGL. Now, we can do OpenTK. This is the standard one that you can do, but it is not written for .NET Core. And so you want to go down to find .NET Standard. Let's see, let's do OpenGL Standard. OpenTK, yeah, OpenTK is what it's called. So OpenTK .NET Standard, this guy works great in .NET Core. If we look around, and it uses .NET Standard, just callable from .NET Core, so we're going to use this guy. The other one says any, but I tried adding it to a .NET Core project and it just threw a fit. So this is what I've been using. So there's my packages. We got .NET Standard. We got system.drawing.common. That just gives us access to bitmaps so that we can do the CPU side of the programming. Let's see here. We're going to need a couple parameters. First off, we're going to need a game window. Let's see here. So create a parameter for the game window. So game window, this is like a win form, but in OpenTK, which is OpenGL framework for .NET Core. And so now we have our game window, and we're going to create a couple other parameters Because if we're going to have a scrolling background, we need to know where in the background we are. So we're going to go ahead and use an offset, an X and Y coordinate, to decide how far to offset it. And again, this is in GPU coordinates, not CPU coordinates. So it needs to be a single instead of an integer, because we're going to have, that value is going to be between -1 and 1, and yeah, and all the values in between, or all the values going to be in between those two numbers. We're going to go ahead and instantiate this game window. So this creates a game window, and here I went with 800 by 600 window. I'm just doing that. You can do whatever size you want. This will just be easy for our testing, since my monitor can easily fit that big of a screen. And then we want to, this game window has a bunch of events. I guess we could do it with events, but I decided to do it the hard way. Now that I'm sitting here thinking about it, I should just use with events. But either way, this is going to work. So I'm adding handlers to these events on it. So we're going to have to create a function for load, Windows resize, and render frame. And like I said, there's no reason why I can't just do it. You can't just do it with events here. I'm just making it harder on purpose, apparently. So let's grab my load function. And we're not quite ready for this yet. So we create a load function. And window resize. And a render frame. So when this thing is running, it's going to the default's going to be 60 frames per second. You can specify a different frame rate if you want. You can do any kind of frame rate that you desire. 60 frames per second is the default. But you can, if you go to the game window, target render frequency, so you can change this to 60, you can change it to 120, you can set it whatever you want it to be, and you can even kind of do multi-threading to some extent. Be very careful with multi-threading in OpenGL, but you can control, you can essentially, you can set it to 0, which would be as soon as it's done, it's just going to start generating, it's just going to redraw again. And so you just got to decide how, depending on the needs of your program, how you're going to handle that. So the first thing we're going to do is we're going to build a content pipe. So let's add the content pipe. And so we talked about these two concepts, the CPU and the GPU. And so this content pipe program or module class is designed to copy an image from the CPU over to the GPU. And so it has two functions, load texture and update texture. Now in GPU land, an image is called a texture. And since we're not directly interfacing the GPU, we're just sending commands to it, whenever we add a new image over to into the GPU, it's going to give us an ID so that it's an integer that we can keep track of that image with. And so let's talk about everything we're doing here. So load texture, we're going to pass in this image that we want to load into the graphics card. And the first thing we do is we're going to call GL. So let's talk about some of our imports here. So this particular method, we're using OpenGL 4 in it. And I'm trying to get better about my programming and writing a more modern GL, and so OpenGL 4 is kind of the latest GL. So this method here is done in GL 4. We're going to use system drawing. We need to use drawing.imaging, and I'll explain why that's important in a minute. And we had a little bit of a conflict here, so we're making sure we're using the OpenGL for pixel format, and we're also importing OpenTK graphics, but it doesn't look like we're actually using that. All right. So you might not need that line. So let's talk about, so we're going to load the texture, we're going to take the image, we're going to take the bitmap, and we're going to turn it into a texture. And so first off, we need an ID for that texture, and so we can ask GL to generate a texture. Technically here with the blind texture, I think you can pass any ID you want in. You just need to keep track of what ID you're using. And so OpenGL offers this functionality that essentially gives you an integer that's not being used. So we're going to bind the texture. So the first thing we're going to do is we're just going to say, hey, by the way, this ID is a 2D texture, and that's what we want for images. So we're saying, hey, graphics card, to get ready, I'm allocating this ID to a 2D texture. Now the next thing we're going to do here is we're going to find the bitmap data, and all this is doing is, so we have the CPU image and the GPU image, or where we want to be a GPU image, and bit-wise they're the same thing. They're just an array of bytes, right? And so we need to get a pointer to the images array, and we're going to send that to the CPU so we can do a copy. So we can copy it from, essentially, from the video card, from your CPU's RAM over to your video card's RAM. And if your video card has its own dedicated RAM, it's going to copy it into its RAM, or if it's a integrated CPU, it's going to, this is literally just going to be copying it from the GPU managed RAM over to the CPU managed RAM. And so by using bitmap data, we're going to get access to the pointer to the image. And so we're going to create a rectangle that's the whole, and we're grabbing the whole image. So 0, 0 to image width, image height, and so that's your CPU coordinate system right there. And we're going to pass in some variables so it knows what format to have the image in, ready for the copy. And now we're going to start setting up some parameters on the GPU side. We're going to tell it that we want to use this linear filter. And so what this is going to do is there's essentially like two kinds of filters you generally use in OpenGL. I think there's more settings if you want to get really particular about how your images are rendered. But linear kind of blends the pixels together. As we talked about, different people's GPUs have a different number of pixels. And so just because one person is at 800 by 600 and someone else is at 1920 by 1080, you're going to end up with, if your image size is bigger than them all or smaller, you're going to end up with pixels that aren't going to be drawn or need to be kind of blurred. And so linear is kind of a blurring of the pixels. You can do, the other common one is, there's linear and then nearest. And what nearest is going to do is that's going to give you a very pixelated image. It's going to try to keep every image in a little pixel square. And so the difference is your image is going to be more pixelated. So linear is more smooth. And so then this is right here. This is the actual command that tell it to copy the image. So we're going to we're putting some formats in. It needs to know the size of the image. So we got the width and the height. And then right here, scan 0, that's the pointer. So it's actually pointing to the block of memory where that array of bytes is that represents your actual image in memory. And this right here is going to push it from the CPU to the GPU. And then we're going to set a couple extra parameters. This is what do you do if this image is oversampled? And what I mean by oversampled is, say, in pixel land, let's say that you have a 10 by 10 image and you go to grab a copy of that image, but instead of passing in 10 by 10, you pass in -10 by -10 or something, so that your request is off the image. By making it repeat, it's just going to repeat the same image over and over and over again. So you end up, no matter what coordinates you pass in, the system will know to return the image of that repeats that way. And so that's going to be very important when we're creating our infinite scrolling background, because we want the exact same image to repeat infinitely over and over again. And so making sure that we setting it to repeat is important. There's other values you can set if that's not what you want it to do. But for our intents and purposes, that's what we're going to do. So this is how you load a texture into the GPU. And when you're done, you're just going to return the ID. So now in CPU land, This should be an integer. Yep. And in CPU land, we've got an ID that represents the texture, and the texture is the GPU representation of that image. Second thing, function that we're going to create in the content pipe is the update texture. And so what this is going to do is take that existing texture ID and you're going to swap it out and say, okay, here's a new image, but I want you to take over that same space. And that's going to be really not so important with the background, since our background isn't constantly changing. But if the background did change, if we wanted to change the background, maybe we're going to a different scene and we want a new background, you could go in here and you could update that background image. More importantly, it's going to be used for rendering of your active graphics. So if you're going to create a frame, depending on how you accomplish your programming, and in my game, I kind of like have a split world where I'm doing half my rendering in the CPU and half my rendering in the GPU. So my CPU is creating this image, and then I'm going to, that's the current scene of the game, and then it's going to pass an entity here to create a frame to actually display it to the user. And so I'm going to keep reusing that same texture over and over again, and we're just going to update it with the new image. And so here we pass in the bitmap, texture ID, and we use the same thing. We need to get that pointer to the image on the bitmap side. And then we're going to use this command, which is text sub image 2D. And so this is going to substitute the existing image with this new image. Okay, sorry. I haven't used this method. This method doesn't have any references yet, so I was just noticing that it's missing a line of code. So we want to make sure that we're telling it which texture that we're messing with. So you first have to bind it to the right texture, and then we're going to substitute this texture that's been bound here with this sub image, and it's the same up here. This doesn't actually specify which texture it's working with, but you have to bind it first. And so that's another oddity of, to me, of GPU programming, is it's all like these series of commands that you're sending. And so this bind texture is very important before you call text subtexture image 2D, otherwise it won't know which texture you're talking about. And so it's important that you bind it, get the pointer. So we bind to the texture that we're looking for. We get the pointer to that image, and then we go ahead and tell it to go ahead and replace this texture, the last bound texture, with this new sub image. And then we're just calling that to clean up this object. All right, so now we have our content pipe. Now we're ready to create our actual renderer. So I'm going to create what I call the classic renderer. And I call it the classic renderer because we're not using GL4. we're essentially using kind of it's a little bit older OpenGL, but it works really great. And I can see that I was doing some debugging earlier, and so we will get rid of, well, we can leave this in here. So this code here, whenever you issue a command to OpenGL and it throws an error, it's not going to actually throw an error. It's going to, like, internally to it throw an error, and then you can check to see if an error has been created. And so you call gl.getError, and then if it doesn't equal no error, then I was having just my code stop so I could help debug it. When I upload this program, I will get rid of all this error handling code. So here's what we're going to do in classic mode. So when we create this new renderer, it's going to send some commands over to OpenGL. It's going to tell it what its clear color is. So every time you render a scene, you first want to start by just clearing everything that's out there. You have to think about it's dual buffering, and so you draw an image on the screen, and then you swap it out with what's currently on the screen. So draw, swap, draw, swap, draw, swap. And so the very first thing you do after you swap, because when you swap, you get the old image back into your your image buffer, and we're going to clear it out before we draw the new frame. And so here we're just saying, hey, use this color. When you do the clear, it just clears it with this color, and you can make that translucent if you need to. I'm just using light gray. It's completely your preference. The user should never see this. This is just depending on what you're doing. So that's how the next thing we're going to do is we're going to set a blend function. And so this is going to be important that when we activate two different textures on the screen, this will be really important since you're probably not just going to have one image, you're going to have multiple images. And so this blend function is going to say when two images are being blended together, how do you decide how to blend those pictures together? And so here, essentially with source alpha and 1 minus source alpha, that essentially means using transparencies. So the alpha is the transparency function in an image. And so here we're saying, hey, use the transparency of the image to handle transparencies. And then we're going to do some enablement. I got a double enable there. And so we need to enable texture 2D. This is important so that GL knows what we're doing. We could be doing 3D graphics. We could be doing all kinds of things. So depending on what you're programming, you're going to do enable and disable different GL features. For what we're doing, we're just doing textures 2Ds, and we're going to be doing blending. And then the next thing we're going to do the matrix mode of the model view. Now this has everything to do with those screen coordinates and how it's being handled by the GPU. In Render Classic, this is a really simple way to handle the screen coordinates. But in more advanced geoprogramming, you're actually going to want to use arrays. So in matrix mode, we're going to be using matrix mathematics in order to draw things to the screen. But in more fancier geoprogramming, you're going to have like an array of matrices, and that'll allow you to bind images to different arrays. We're just going to do it basic, or this is more basic. And load identity, that gets that basic the basic matrix up and loaded, and you'll see how that plays into it. So here I created a couple methods. I created a start frame method so that we know we're starting a new frame, and the very first thing it does is go ahead and clears the color, and we're saying use the clear color from that we set right here. So this command here is going to clear it using light gray. Viewport is important. So Viewport is how to explain this. It's imagine the user is going to resize their screen, and so they make their window a little bit bigger or a little bit smaller, and we want our 100% image to fit into whatever width and height that their screen is. And so this is using essentially CPU coordinates. And it's saying, okay, design the view to be this width and this height. And so now all of our coordinates inside the GPU from -1 to 1, it now knows that they are 0 to this width, 0 to this height. And so every time the user resizes their form, if you want your graphics to change size with their stretch, then you need to update the viewport, and you can change that anytime. I usually will show you up whenever we'll put it on the resize event of the game window to just call it the adjust view. Here we're going to set the background image. So we just call it set background. You pass in an image, and we in here we have a background image texture ID. And so again, this is just to keep it very basic. We're just going to use two textures. There's the foreground texture and the background texture. And so right now we're just messing with the background texture. I'm defaulting it -1, just so that we know it hasn't been bound yet. because it's always going to return the gen texture ID is always going to return a positive integer. So we go ahead and set the background texture ID to the image that we pass in here. So now we're going in there, as we saw earlier, and we're copying whatever image we loaded, we're passing in is getting loaded into the GPU, and we're getting the ID of the texture. And now we've got a function here to run to the background, and we've got an offset X and an offset Y. And I'm going to explain to you. So here, since we're using the identity matrix, we're using kind of the default built-in matrix. When we want to transform different images, we're going to want to do the math against those individual images, and then we might want to go back to and then when we're done, we want to go back to the basic matrix. And so we accomplish that by pushing and popping. So we're saying from this point forward, so we're binding the texture to the background image, and then we're going to push it. And so from this point forward, all mathematical commands are going into a different matrix. And so here we're telling it to scale. And so this is scaling by 0.5. So whatever image we put in, we're going to scale it by half. So now we're shrinking the image by half of its size. And it's got an X, Y, and a Z coordinate, and we just make the Z coordinate 1 since this is just 2D graphics, so we do X, Y, Z. And then we have the translate, and that's going to move the image around on the screen. So we're translating it by X and Y. And then we have our normal render, and we have our Nora render, what I call a Nora render. The normal render is just going to be 1 for 1. It's going to render a single copy of the background image. The Nora render, however, is going to take advantage of that repeat command that we used. So inside our Nora render, so let me just talk for a second about the normal render. So normally, there's two different coordinate systems. There's the texture's coordinates, and there's the screen's coordinates. And so the texture's coordinates are here, and the vertex coordinates are there. So that's the screen coordinates. So the bottom left of the picture. Oh, and one other funny thing about GPU, when it comes to actual images, they're like they're reversed or rotated. And so you have two ways to handle this. Number one, you can flip your image so that its coordinates are exactly the same as the vertex coordinates, or you can do kind of a cheat here, and you can swap your text coordinates around so that it renders the image flipped, and then you don't have to flip it on the CPU. You can flip it on the GPU. So that's what I've done here. So the bottom left of the text coordinate is 0, 0. The texture is 0, 0. And the vertex is -1, 1, yeah. And so, yeah, again, this is true. Once again, the intricacies of GPU programming. The bottom left corner of a texture is 0, 0. The top left vertex of the monitor, your top left coordinate of your monitor is -1, 1. So here, -1, 1. 1, 1 for the top right, 1, -1 for the bottom right, -1, -1 for the bottom left. So we're saying this is normal render is fill the screen 100%. Now, Nora render is fill the screen 200%. So we take all those corners, and and this is just on, so the vertex should be the same. So if we look at our vertex, so we're on the screen, we're saying -1, 1, 1, 1, 1, -1, 1, -1, 1. So this is the same. This is essentially saying 100% of the screen. But our image coordinates have doubled I've added 1 to each corner, essentially, or depending on the corner. So the top left corner so let's go to the bottom left corner. So before the bottom left corner was 0, 0. Now we're saying the bottom left corner is -1, -1. And so that puts it out 1. So what happens, the result here, by pushing all 4 of the corners out by 1, because we have the repeat, we're going to end up with with a grid of 9 copies of the image, and I'll show you what that looks like here in a minute when we finish writing our main program. So the basic idea is the NOR render is going to create 9 copies of the image in a grid, and the reason why I do that is so that we can have the infinite scrolling, so that when we're really close to the edge, we see the next image coming in. And then right when you flip it over the edge, I'm going to use something like a mod or something to swap you back to the beginning of the image. I'll show you how we do that in a second. Okay, so that's our renderer, and this is all we need for the GL. One other thing, I'm checking the keys. So this is the way that we make the image scroll. So every refresh, we're passing in the X and Y coordinate, which is essentially our offset coordinate of our background. And I'm just using OpenGL to check if any key is pressed. And I'm using W, S, D, and A, which are kind of your basic up, down, left, right keys on your keyboard. You can do whatever you want. You could actually use the arrow keys, but this is just good for our testing. And if you're holding down W, we're subtracting 0.0025, because again, it's all in these percentages, 200%, so you don't want to move it too fast, too slow, so that's what I came up with. That was good. And then here we're actually flipping it, so you can use a mod. For what I'm using in my actual project is a couple of mod statements that figures it out. But this particular, for this to work, I just did, hey, when you're at 1/3 of the screen, because remember it's a 9 by 9, so 1 frame of the 9 by 9 is 1/3 of the total screen. So this is just saying, hey, when you cross the 1/3 barrier, swap it for the negative value, so that jumps you back to the other side of it. It's kind of like a mod statement, but not exactly the same. So that's everything we're doing. I don't think there's anything else in here. So let's use our classic renderer here in our program. So we've got all these events. So when the form load, this is like we need to create our object. So I'm going to go ahead and create our classic. So when we start it up, this is just like a form load event in the WinForm. So when this form is loaded, we need that to run. So GameWindow.run. So that is like in normal WinForms, that's form.open or load or whatever it is. So this will cause the form to this right here is blocking, and so the code's going to stop right there, and it's going to load that form on the screen. And the first thing it's going to do, it's going to call this load, and so we're going to initialize our renderer. It's going to set all those GL properties we saw in its new statement, and we're going to set the background. So here I've got a NASA image of a galaxy. And so we're going to set that as the background. We've got the window resize. This is important because this will get triggered when the form initially loads, so the graphics card can know the size of the screen in pixels that it needs to render everything into. And then we have this render frame, and this is going to be called based on that update frequency. We haven't specified an update frequency, so the default is 60 frames per second. So this is every 16.3 or 16.6 milliseconds, I think it is. This is going to get called. And we're going to just check the keys so that we can do that offset. And then we're going to start the frame, which we saw it just clears it out. We're going to render the frame. We're going to render the background. Let's just go into that real fast. Yeah, so we talked about that. And so currently, right now it's going to be half. The image is going to be half the size, and it's going to be the NOR render. So we're going to see be able to see 9 copies of the image on the screen at the same time. And then this is where the double buffering comes in. We're going to swap it out. So we're going to clear the buffer, draw the buffer, swap the buffer. Easy peasy. Let's see how this looks. And there we go. So the image is just one image, but we told it we oversampled it, and so we increased each corner by half, and so we end up with 9 copies of the image. And let's see, if we multiply it if we zoom in by 3, then we should only see 1 image. So let's scale it by 3. So now we have it. Now when we start hitting the WSDF, we start scrolling. And so that's why we do the repeat. So then when we hit the border, it jumps into the next image. And let's see here. So now we're going to zoom way in. So we're going to scale it to 15. So now we're zoomed way in, and now we're going to scroll, and you're never going to know when we actually do the flip, because it happens when we hit that 1/3, with 1/3 of the images all the way through. It flips the coordinates, and you can't even tell. If we switch back to the small scaling, you'd be able to see it doing its thing. So this is back when we get to the edge. Yeah, it's just repeating the same image over again. But lined up wise, it's perfectly lined up. So you can see as it jumps over the threshold there, the images are all lined up, and so that's why when we zoom it in, you just don't see. You can't see this stuff when it's all zoomed in. I think it should work. Scale times 3 perfectly. Let's find out. Yep. So you're reaching that edge of the screen here, and then it's switching you back to the center, but you can't really, the user can't tell that image has jumped because you're zoomed in too far to be able to see the edges. So it just looks perfect. And we can up, down, left, right. There you go. So I'll include this all the source code as a link on this video, and feel free to ask me any questions, and we'll get into part 2, actually rendering a frame of your video game into OpenGL. Thanks a lot.